little bit about his background, which happens to overlap with some of mine, although in different decades. So Mark did his PhD with Brooke Benjamin in 1993 and was in Bath with John Tolland, I guess as a postdoc, is that right? From 93 to 95. And then a long spell in Loughborough between 95 and 2007, and has now ended up in Saarbrücken and Saarlandes University, is that right?
That's correct.
Okay, since 2007. So the talk, as you can see, is doubly periodic traveling waves with connections to hydrodynamics and elasticity.
Thanks very much. Yeah, so this, in fact, is only the second live talk I've given since the lockdown was over, so it's probably going to be a little more nervous than usual, but you'll see. Okay, so the title I advertised was actually doubly periodic traveling, gravity-capillary and hydroelastic waves. I'm going to focus on the hydroelastic today because it's new. To be focusing more on the idea than on the actual details of the mathematics. I thought that would be nice. Okay, but here's the picture of what we're talking about. This was a picture which was given to me by Diane Henderson. And the only condition was that I told everybody it was from her. You can see this is a doubly periodic traveling gravity capillary wave. So you can see the waves are periodic in this direction and also periodic in kind of this direction. So you get this nice periodic box, the wave repeating itself. I guess the direction of travel is along the tank in this picture, but I don't actually know. So this is just to focus the ideas what I'm actually talking about today. And this is the nicest picture of that I have. I looked everywhere for a really good picture, and then I asked her, she immediately gave this picture from her wave tank.
So, quick question: how many phases from left to right? Is it just one?
That I don't know.
Looks as though they might all be slightly out of phase.
I mean, it's supposed to be purely periodic in two directions, but of course there's some kind of interactions from what's going on. So, okay, so this isn't supposed to accurately depict what I'm talking about. Just give you an idea. Okay, so let's come to the equations themselves. I think probably everybody here knows these equations. Katie presented them last week in her talk. So we're talking about a 3D perfect fluid. So the coordinates here are x, y, and z. Finite depth. So bottom is a y0. The free surface is then h plus graph of a function eta, which depends on x, z, and t. We'll do incompressible irrotational flow, so that the velocity field is the gradient of the potential, which is harmonic in the fluid. And then you come to the interesting part of the water wave problem. We've got these two nonlinear boundary conditions at the free surface. So this is the kinematic boundary condition. Like this condition, it's basically the condition which defines the surface. It says no water passes through the surface. And the dynamical boundary condition is the condition of balance of force at the free surface. Now, what's the U? So I've got two versions of the problem here. So the first is the water wave problem, in which case this U is the curvature of the surface. And in the hydroelastic problem, this is a problem where you have a thin elastic plate over the surface, supposed to be a thin ice sheet. And in this model, then U is given by a different function of eta involving high derivatives of eta. What U actually is isn't actually important, but I will show you the horrific formula in a moment. Okay, so G is the acceleration due to gravity, of course. Now sigma, if it's water waves, sigma is the coefficient of surface tension, and if it's hydroelastic waves, then sigma is the coefficient of rigidity, or flexibility, or what I can't remember exactly what this coefficient is called. It's usually denoted by D, but I wanted to keep things kind of the notation uniform. So I've cheated a bit and called it sigma here in the same way. Okay, and here are the difficulties in the water wave problem, which we all know. It's a free boundary value problem. You don't know eta to start with, and then you've got the two hideous nonlinear boundary conditions at the free surface. Okay, so let's take a look at, I'll just show you the formula for U. It's not important what it is. I mean, it is when you do the mathematics, but for today's talk, it isn't. But we're all friends here, so I don't want to hide anything from you. So here it is. So if it's water waves, U is just, well, minus the curvature of the free surface. And if it's hydroelastic waves, then this is the formula for U, which you see is a much more complicated function involving higher derivatives of eta. Altogether, the highest derivative here is fourth order. So the modeling, it's the standard model for water waves, and the modeling for this comes from Plotnikov and Toland in their papers about 10 years ago now when they discussed various models of that. So any criticisms about the model is to be addressed to those guys, not me.
Do you have a postal address?
Or complaints in triplicate. Okay. So what I'd like to do today then is to discuss two different types of existence theories for traveling water waves in the context of hydroelastic waves. They both pass over. Here they are. You can use spatial dynamics. This was a method which I developed with Haragus. There's also a method based upon Lyapunov-Schmidt reduction, which goes back to Craig and Nicholls. I mean, as you can see, we worked on these roughly the same time. They came out at the same time. Now, there are actually problems with both of these theories. And what I'd like to do today is to honestly tell you what the problem is, including my own work, and show you how to fix it. And in the case of Craig and Nicholls, maybe saying there's a problem is a little bit too harsh. It's actually that you can simplify their method quite a lot. Yeah, there's actually a slight error in our paper, but it's a constructive error, which is the fact we made the error leads to a huge improvement later. I think if we hadn't made the error, we would have come across this. Okay, so let's start then with spatial dynamics. And the work I'm going to talk to you about is cooperation with my PhD student, Hamid Ahmad, and my postdoc, Dag Nielsen. Okay, so what's the idea in spatial dynamics? So the idea in spatial dynamics is you look at a problem and formulate it as an evolutionary system that the role of the time-like variable is taken by a space variable. Now, they do this all the time when, for example, you look at solid true waves for KdV. You write it always as a dynamical system or a ODE in which x, the horizontal direction, plays the role of time. So to this audience, this is nothing new. But the point is that x could be any unbounded direction. It doesn't have to be the direction in which the wave is moving, for example. So what I did with Mariana was this. So what you're looking at here, you're looking down on the free surface of the water. So you've got this kind of infinite, you're looking down on a plane essentially. And then you've got two directions, x and z. Those are the usual Cartesian coordinates. And you choose two other directions at random, if you like. Here's x, and z. Theta 1 and theta 2 just tell you the directions in which they're pointing. And you say, okay, I'm going to use this direction, capital X, as time. And in my second direction, z, I'm going to look at waves which are, say, periodic in that direction with a fixed period. Okay, so, and then you somehow, by a trick which I'll show you in a moment, formulate your problem as an evolution system of this kind in which this x is the time-like direction, and this you have a phase space of functions which are periodic in z. So every point in your phase space corresponds to a wave profile which is periodic in z, and a solution of this is kind of a trajectory through this phase space, every point of which gives you a wave profile which is periodic in z. Now the point here is, if you have a periodic solution to one, so this is supposed to be, so in your mind now you're in this infinite dimensional phase space, one, and you're kind of circling the origin. It's a very idealized periodic orbit here, as you can see. Now, obviously this is generating a periodic wave in the x direction, but every point on this circle corresponds to a wave profile which is periodic in z. So a periodic solution in x to this gives you a doubly periodic water wave. The periodicity in x comes from the periodic solution, and the periodicity in z comes from the fact that you're in a phase space, each point of which corresponds to a wave profile which is periodic in z. I wanted to do a nice computer animation showing you how this thing generates this, but beyond my technical capabilities. Okay, so this is the idea in spatial dynamics. Formulate your problem as an evolutionary system with some direction as time, and in a second direction, a phase space which is periodic in that direction. Periodic solutions of this will then give you doubly periodic waves.
So let me simplify straight. So this is still propagating in physical x direction.
Propagating a physical x.
So this entire pattern, which is jiggling around,
going this direction. Yeah,
okay.
That's right. Yeah. That's a good point, but the direction of propagation doesn't have to be this x or this z. It could be anything. No?
Sorry, Mark, your
you are discussing here the problem in the space variables. You're not connected yet to the original problem where you have the evolution in time.
There will, I mean, I'm always going to talk about traveling waves, in fact, so they're always going to travel.
Okay, so it's a stationary
Yeah.
time. So,
Yeah, this will come up more clearly in the next.
yeah, just to,
Is there a restriction on the period you can pick for your transverse Z rotated coordinate?
No,
Or is that full continuous?
not yet.
Oh.
At this moment in time, no, but it might be later. Okay. All right, so let's continue. So first, let me first give you an idea. Well, the first thing is, well, this is all very well and good, but how might you formulate those equations I showed you in this form? It's not really obvious how to do that. So here are the equations again, and this time I answered the question just asked. I've now gone to traveling waves in the x direction. So you see the wave equations, they change a bit, and you've got the d by dt changes into minus c d by dx. And again, I'm hedging my bets with the u. So it could be water waves or it could be hydroelastic. Let's suppose it's hydroelastic. And the point here is that those equations follow from this variational principle. This is a version of the variational principle by Luke in JFM 1967. He had specialized it to the equations for hydroelastic waves, the Q and the P with those hideous formulae I showed you before. If you take variations in phi and eta of this and set them to 0, you will recover these three equations. Okay, and if it's water waves, you just have to change this to the appropriate thing. Okay, so you see what happened there? I'm non-dimensional. Okay, so this means that now the parameters here are alpha and beta, and they're alpha and beta here. And so these are the parameters in the problem. Alpha, 1 over the square of the fluid number, and beta is some kind of Bond Weberish number, which is the coefficient of rigidity. Is that what we decided it was? So, and that means that the height is also going to 1 as well. Okay. All right. So the key here is you've got a variational principle. Okay, so this is just a sketch of what to do. I don't want to go through all the details. You can do this explicitly, what's on this transparency. And it's a running joke in these talks. I always claim that students of certain levels can do this calculation. So PhD students can certainly do it, otherwise they wouldn't be a PhD student of mine anymore. But a good master student should be able to do this. So here's the idea. So first of all, you obviously want to change the variables from Cartesian to these oblique coordinates, the ones you're interested in. That's just what this is. The new here is a normalization in Z, so that now we can look at waves which are just 2 pi periodic in Z. That's the whole point of the new. So new measures the frequency in Z. And another thing you want to do is you want to avoid the problem of the variable domain. And you do this by using so-called flattening transformation. You introduce a new coordinate capital Y, which is the old Y scaled by the height. And when you do this in the equations, you get nastier equations, but they'll be on a fixed domain 0 to 1 instead of 0 to 1 plus eta. Okay, so this is what they're saying here. The new variables eta tilde and phi tilde are the old ones, simply with this change of variable. You go to the oblique coordinates and you scale 1. Okay, and you plug those into the variational principle, and it gives you a new variational principle. And the variations of the new variational principle give you the old equations to the scaling. Now I can write them all down, but it takes kind of 3 transparencies to do this. I mean, they're nasty equations. I did actually have the formula for L explicitly, but then I killed it again. Okay, what you need to know is simply the structure here. The variational principle looks like this. So X is a kind of distinguished direction, right? It's the time-like direction. And the variational principle, you can think of it as an integral over X of a function of eta and phi, and then time derivatives of eta and phi. Now, this should remind you of the principle of least action in classical mechanics. Undergraduates now, well, it used to be in my day, I'm not sure anymore, but and if you have an action functional like that, you can do a Legendre transform. So I've got a higher order derivative here, eta xx. But if I didn't have it, you know what to do. Then this would be like Q1 and Q2. This would be Q1 dot, Q2 dot. Then you introduce the P's. Those are the derivatives of the L with respect to the Q dots. The Hamiltonian is, how does it work? The PQ dot minus L. And then you write down Hamilton's equations. So you can do exactly the same thing here. You introduce momenta, which I've called here those are these two, exactly, and do a Legendre transform, then you can find a Hamiltonian formulation of your problem with x as time. Now, the only difficulty here is you've actually got a second derivative in eta, so you need a higher ordered version of the Legendre transform. It was actually quite difficult to find this, but Brooke saved me. In one of he's got an enormous paper in '84 called something like Flow Force and Variational Principles, which everything you ever wanted to know about Hamiltonian systems is in there. And he's actually got a reference to the Legendre transform with higher derivatives, which gave me exactly what I wanted. Okay, so the message here is you can indeed formulate your problem as an evolutionary equation with x as time, and in a phase space where everything is periodic in Z. I did say I wasn't going to give you the details. This is just a sketch of how to do it. So this is homework. Tomorrow morning, 9 o'clock, please. Like the details of this written out. So it will be graded, and if you do badly, it will be deducted from your expenses. Okay, but really, this is something you can do explicitly. If anybody really wants to see the formula, just ask me later, and it will be in the paper. Okay, so now you have successfully formulated your problem as an evolutionary equation. And now the question is, what we'd like to find, remember, is periodic solutions to this equation, periodic in X, because they will give me doubly periodic auto waves. Okay, so the tool you want here is the Lyapunov-Schmidt theorem. This is a classic theorem for finding periodic solutions of Hamiltonian systems. And there are infinite dimensional versions of it. This is how it works. Non-resonant eigenvalues. So if this was a linear problem, there was no n, you just had a linear operator L, and you had a pair of eigenvalues plus or minus I omega. Non-resonant means no other eigenvalues are integral multiples of them. Then you would know that there'd be a family of periodic orbits that are exactly circles surrounding the origin with exactly that frequency omega. And the Lyapunov-Schmidt theorem says that's correct as well for a nonlinear system, which is Hamiltonian. You don't get exactly that frequency, you get a family of periodic orbits, small amplitude, parameterized by their amplitude. As the amplitude goes to 0, the frequency tends to that. Okay, that works in an infinite dimensional setting as well. So here I've got a case where you got 4 purely imaginary eigenvalues, and if a pair of them, say these two, are non-resonant, then you can apply the Lyapunov-Schmidt theorem. It will give you a periodic solution to this, which will generate the doubly periodic auto wave like we saw before. This part here is meant to tell you that because it's infinite dimensional, there will be more spectrum than just purely imaginary eigenvalues. And there's a technical condition which you need, which says, well, the rest of the spectrum has to be bounded away from the imaginary axis in regions which look like that. So this is just to remind you not to get too carried away with this connection with finite dimensional Hamiltonian systems, because it is actually a PDE that we're solving. And this does cause technical problems which are massively under the carpet at the moment. Okay, all right. So now our question is, can we find non-resonant eigenvalues? Because if we can find those, we can apply the Lyapunov-Schmidt theorem and we can find periodic orbits. Okay, and so now here's another quick calculation you can do. So this is actually an equation which says, I'm going to now look for eigenvalues of L, purely imaginary ones. Here's the eigenvalue I omega. And because everything is periodic in Z, at linear level, I can expand in a Fourier series. And obviously, the eigenvectors have to belong to one of the Fourier modes. It will all decouple. So this is saying, here I'm in mode K, you see e to the ikz, everything's 2 pi periodic in Z. So you're in mode K. The Vk is the eigenvector is actually Vk e to the ikz, precisely. And omega is the eigenvalue. Okay, and what you find is you just do a calculation and you get a solution like that, if and only if the omega satisfies, or the omega and the k satisfy this equation, and here where L1 and L2 will give you my these combinations of omega and k. See, there's nothing new here. You've really just got alpha and beta, those are the parameters. You've got the frequency in the Z direction nu, you've got k, the Fourier mode here, and the omega, the eigenvalue. It's just, and then the angle theta 1 and theta 2, but it's just all the stuff you've seen before. This is just written in a compact form. Okay, so now we come to really the nice thing about it is, why did I write it in this way? And the answer is this gives you a really good interpretation of how this works. So you see, if you now think in the L1, L2 plane, this describes some geometric object in the L1, L2 plane, which I've called CDR. DR stands for dispersion relation. It's actually just the classical dispersion relation in 2D, Cartesian coordinates. And these two guys, L1 and L2, they just describe a line in the L1, L2 plane. So what we're looking for is intersections of lines with the dispersion curve. And every point of intersection will give us a purely imaginary eigenvalue. So here's an example. So on the left, you can see the dispersion curve in the L1, L2 plane. So L1 is across L2 up. It can have three possible shapes. It could actually just be empty. I mean, there could just be nothing. Just zero is excluded from this analysis, and zero is always there. Otherwise, you get one of these three shapes. You kind of get like two O's, or I don't know how to put this, like two O's kissing, and then sort of this sort of shape. I really don't have a word for that. You know, two hair drops. If you sorry,
Ears.
Yeah, two ears. Let's say ears. Yeah, yeah. So two ears or three ears kissing, or two O's. Yeah. And so here you see these are the lines I was talking about, the K's. And on this you can see examples of when the K's cross the dispersion curve, and every intersection corresponds to a purely imaginary eigenvalue. I mean, it's a wonderful picture. So just a bit about the structure. So the K's are all parallel lines. Distance between them is kind of determined by nu. That's the period in Z. The bigger nu is, the wider the gap between them. It's not exactly nu, but it means proportional to nu. Theta 1 and theta 2. Well, theta 2 tells you what the gradient of these lines is. There's actually another line called L, whose gradient is theta 1, and this determines the magnitude of the purely imaginary eigenvalue. So let's see how to work it out. So this is line 1, so it's Fourier mode 1. So there are two purely imaginary eigenvalues in Fourier mode 1. There are two in Fourier minus 1. Now that has to be because it's a reality condition. You know, you have to have complex conjugate pairs. And here I've got 2 in mode 2, and 2 in mode minus 2, and 2 in mode 0. And if you want to work out the actual magnitude of them, what you need is the distance to the red line along the green line. So this distance is the magnitude of that eigenvalue. This distance is the magnitude of that eigenvalue. This distance is the magnitude of that eigenvalue, and so on. You can read all the information off this picture. I know this is a lot of information to take in, so there's no quiz on this right now, but you get the idea. The idea is simply that you can read all the information off this picture. And I mean, this is really super cool. And I have to confess, this was Mariana's main contribution to this. She came up with this idea of this wonderful geometric idea.
This arrangement is so it's not generic. I mean, for example, the line K0. So it crosses the origin. The origin is not.
The origin is excluded from this analysis.
So
Yeah.
can you have a gap
Yeah.
between the two? So
you could have this, and
eigenvalues.
yeah, you could have this, and you could have, say, K0 going through the origin and K1 and minus 1 out here. So there are no purely imaginary eigenvalues. You can have that. You can pretty much have anything you want.
Okay.
Pretty much anything you want. I used to give a talk on this in a different circumstance, in which I said this is kind of a paradigm for bifurcations in Hamiltonian systems, because you can actually get pretty much anything you want like this. So I don't know if that answers the question. It's generic and non-generic in a sentence.
I think the question has to do with the two circles shape. It looks as though you get 4 eigenvalues for K0.
Yes, you could do it. Yeah, that's right.
So this goes down to the gap between.
Mhm. Yeah, that's right.
The period.
That's correct. That's exactly correct. Okay, so now we're armed with everything we need, right? So let's now actually do this and construct doubly periodic waterways. All we have to do is find the intersections of these lines. They'll give us purely imaginary eigenvalues. Just check that there's no resonance. And we got doubly periodic waterways. You can see by my voice that there's a catch, right? You can wait for it. So I'm going to do this 3 times. I'm going to do it wrong twice, and then I'm going to do it right. Okay, so here's the first attempt. Yeah, so as you can see, this is a wrong version. Yeah, so this is obviously wrong. So let's see. So here, I mean, again, I've just chosen the form to look like the two ears. We decided it was ears, right? Yeah, so, and here I've got what Antoni talked about, the K0 intersecting twice. Okay, so you might think, okay, well, let's look at omega 1s. Now, supposing omega 2 is not an integer multiple of omega 1, then I've got the non-resonance condition satisfied here, and so I have a family of doubly periodic water waves. Okay, but you see, this is wrong, or at least not entirely right, because doubly periodic isn't doubly periodic. Think about what's happening here. So K0, go back to the linear level only. So this is Fourier mode 0. That means we found a solution which looks like this. See, the 0 is the mode in Z. The omega 1 is the eigenvalue itself, right? So you see, in fact, e to the complex conjugate because of the reality condition, e to the I0Z has the unpleasant property of being 1. So in fact, at the linear level, and then also at the nonlinear, we've actually only found waves which depend upon X. So it is a doubly periodic water wave, but in a trivial sense, it doesn't depend upon the second direction Z. Now, Eric Vallian kindly called these 2.5-dimensional waves. I think this was to save other people from embarrassment, not me. Marianne and I did not make this mistake. We saw that this was obviously the case. But you have to, it just shows you have to be a bit careful with this. All right. Now here's attempt 2, which is also wrong, but more subtly wrong. And Marianne and I did not see this. It was all her fault, you know. So here's attempt number 2. So this time, we alter the parameters so K0 doesn't intersect. Now we got no possibility of having this zero mode around. And we got modes 1 and -1. And again, you can see the structure a bit more clearly here because of the reality condition. If you've got omega 1 in mode 1, you have to have minus omega 1 in mode -1, and so on. This is just a reality condition. So let's take these two and suppose that omega 2 is not a multiple of omega 1. So this is saying, and then you say, okay, Lyapunov-Schmidt theorem, I'm going to get a periodic solution of that, which will give me a doubly periodic water wave. This is also wrong, but for a more subtle reason. So again, do what we did before. Look at the linear level. So it's mode 1 and I omega 1, X, plus complex conjugate. Those are the ones that's coming from there. If you want to write it explicitly, you know, it's A bar e to the minus I omega 1 e to the minus IZ. But if you do some algebra here, you see this is just actually omega 1x plus z. So again, at linear level and in fact at nonlinear level, they only depend on one horizontal coordinate, but this time it's a bit more sneaky, you see, it's not x, it's omega 1x plus z. Yeah. So again, you have found 2.5-dimensional waves. Now that's annoying. And we actually made this mistake in our, well, we sort of did and didn't at the same time. We kind of said, oh yes, I know you can use the Lyapunov-Schmidt theorem, which is correct. But we didn't point out this particular problem. And in fact, I became aware of this shortly afterwards, but I thought, well, you just have to use a resonant version of the Lyapunov-Schmidt theorem and you can fix it. So here's the correct attempt. What you actually have to do is you have to look at a situation where the two eigenvalues that you get, let's look at 1 and -1 again, they're actually the same. Right? So instead of getting omega 1 and omega 2, you get omega 1 in mode 1 and -1, and you get minus omega 1 in mode 1 and -1. So you get a so-called 1-to-1 resonance here. Now, you might think, well, this is what we didn't want before. We didn't want this is the worst kind. It's not just that omega 1 is a multiple, that omega 2 is a multiple of omega 1, it is omega 1. And so the idea is that if you had a resonant Lyapunov-Schmidt theorem for a 1-to-1 resonance, then you could use it. At a linear level this time, you see, when you do the same thing I did before, now you get two combinations. So here's mode 1, here's mode -1. They both have omega 1s. That's complex conjugate, and now you cannot write everything as just a function of one variable. And so you really do get a doubly periodic water wave, and you are now happy. And so I thought, well, okay, so all I need to do is like look in the literature and find the resonant version, because I knew there were resonant Lyapunov-Schmidt theorems. Well, good luck to you if you do this, because you'll find there are versions. There are some in the 70s by Churchill and Kummerer, There's some recent ones by Lam and Lutzi, by Montaldi, but none of them are general enough to apply to this situation. So in the end, we actually proved one ourselves. It's purists might say that what we did is actually not quite a Lyapunov-Schmidt theorem, because we actually use an additional parameter in the Hamiltonian system. You've got loads of parameters around here, remember? You've got alpha, beta, nu, theta 1, theta 2. So introducing a new parameter is not a problem. That's what we did. We actually used one of the other parameters to find these doubly periodic solutions, which means it's not, purists would say it's exactly a Lyapunov-Schmidt theorem because those don't have extra parameters. But it's a theorem with a wide range of applications, not just to water waves. And this is the work which I did with Dawn and Harmy. Okay, and it may be that I pursue this and we will actually prove a genuine Lyapunov-Schmidt theorem without additional parameters, but we're kind of going, off topic then. What we wanted was just a cheap and cheerful theorem to solve this problem, which we now have. Okay, so that's a summary of the first method, spatial dynamics for doubly periodic waterways. That's how it works, and that's what you have to watch out for, these 2.5-dimensional waves, which are a real pain because they can slip under the radar, Okay, so time for a change of scenery then. So you must say, this spatial dynamics looks like that. It's all a bit, and Walter definitely didn't, Walter Craig. Walter Craig was a former mentor of mine. I wrote my first paper with him when I was a PhD student with Brooke, and later on there was a bit of tension between us because we're working on different methods, similar problems, and it's obvious, really, right? Later on, you're former mentor, then you become colleagues. But it was such a shock when Walter passed away 3 years ago. And, yeah, all I want to say to the younger people is here, you will have tension later with your mentor. Make sure your mentor knows that you appreciate them, because it could be too late. Okay, so here I want to reappraise the method of Walter Craig and David Nicholls. This is work with a master student of mine, Ellen Dissimona. This is a very, very gifted master student, in fact, who I hope I'm going to retain as a PhD student. But he's one of these ones, I don't know, I have to think about it. All right, so this is a different method for doing the same thing, but it is closely related. Okay, so again, let's just take a look at the equations. These are the same equations as before. This time, instead of taking the direction of the traveling waves fixed as x, I allow it to travel in a direction which is maybe not x by having the speeds c1 and c2. There's actually no loss of generality in saying it's x, because before you go to traveling waves, the stuff is rotationally invariant. But here, what Walter and David used, they used two directions, c1 and c2. Okay, so when you substitute those into the equations, that's what you get. And I've already non-dimensionalized here. So the gamma is, as given here, you see G has become 1 and the depth has become 1 due to non-dimensionalization. It's a different non-dimensionalization to before. I apologize for this, but I wanted to keep the harmony between the two approaches. So I used my non-dimensionalization with Mariana in part 1, and in part 2, I used David's with Walter. Okay. And I think most people here know the Sakharov-Craig-Sulim trick, which again, you want to get rid of the problem due to the variable fluid domain. And I did it in the previous thing by just flattening. And the Sakharov-Craig-Sulim trick is to use a Dirichlet-Neumann operator. So it's defined like this. So here's a Dirichlet problem. Solve Laplace's equation with Neumann data at the bottom and Dirichlet data at the top. Psi is given. And the Dirichlet-Neumann operator is the operator which works as follows. You feed it psi, and it gives you, in return, the corresponding normal derivative of phi of the free surface. And usually you multiply that with this normalizing factor. It's not necessary, but it makes certain formally later on a bit clear. Okay, and in fact, in using this, you can reformulate these equations as equations for eta and psi. Here they are. That's the Sakharov-Craig-Sulim formulation. And here's another thing might interest you. we're talking reminiscing about the past. Walter Craig was actually working on that when I was a PhD student. So I'm one of the few people who saw pre-publication versions of the Craig-Sulin paper in 1993. Witnessed the discussions about it. It was a fascinating time. Okay, here they are. Now, so what David and Walter did was they looked at these equations, the two of them. They used a variational formulation of them and did a variational Lyapunov-Schmidt reduction. Now, what I want to say today is that you can actually do this more simply. You don't need the variational structure, and moreover, you don't even need the two equations. So just look at this naively for a moment. If you look at the first equation, you see you can write psi as a function of eta like this naively. I mean, supposing we can invert the Dirichlet-Neumann operator, you know, I mean, it's very naive at the moment. And then substitute psi into the second equation, and then you'll get a single equation for eta. Yeah, and the L, which you see here, is just, this is where the inverse of the Dirichlet-Neumann appears. Okay, now I just maybe want to say something about the notation. So when I write nabla, it will always mean just in X and Z. So the point here is there's no Y dependence explicitly, but I haven't, it's still there. It's in the definition down here because this thing is a highly non-local beast. Okay. All right, so in fact, you can write this as one equation, which I'm still going to call the Sakharov-Craig-Sulin formulation. No, because I mean, it is their equation. It'd be cheeky to say otherwise. It's just that they didn't reduce it to one equation. Yeah? So last week, Katie gave us a lot of alternative formulations of the water-wave problem as one equation. And this is just another selection of the many. But for my purposes, it's extremely useful. So I'm going to show you a theorem now, and I'm probably not going to get around to proving it. I put the proof at the very end, but I'll probably not put but here it is. Oh no, sorry, I messed the order up here. Let's do this first. So let's first talk about doubly periodic waves, how to represent those. So this time you do it in a slightly different way. So doubly periodic means that translations of X through a period will always give you the same thing. And the period is anything in this lattice. So you do it like this. You take two basic directions, P1 and P2, and then you form a lattice of points in the directions P1 and P2. So this is P2, this is 2P2, P1, 2P1. This is P1 plus P2. This is P1 plus 2P2. You can still do it, right? And so what you want is periodicity in this sense. Okay, and you can represent functions in Fourier series with respect to this lattice like this. You sum over wave numbers in the dual lattice, and the dual lattice is defined as follows. So again, it's then integer combinations of L1 and L2, where the scalar products of the P's and the PI's and the LJ's and the 2 pi delta J. Yeah, so it's just a dual lattice. So again, you don't need to remember the definition as a dual lattice, just remember that it's what enables you to write down a generalized Fourier series. This is just a generalization of the usual Fourier series with respect to a periodic lattice. If you want to know how the function spaces work, this is, I've been very good. I haven't done much function analysis, it's too early in the day for that. But this is how you define the subnet space HS on a basis cell. It's defined in exactly the same way as it always is, in fact, the Fourier transform with this weight, the sum has to be finite, and this gives you the norm in S. And you can do this then for any S, positive or negative. We don't have to do positive values. I'm not going to talk about function spaces at all. I just want to show you how it all fits together very, very nicely. And my student, in fact, in his master's thesis, he wrote, in his bachelor's thesis, in his master's thesis, worked out the full theory of sublet spaces in this sense, just using the definition, which I thought was kind of a remarkable thing for a bachelor student. Okay. So all you need to remember here now is you've got the lattice, the basic periodic directions of P1 and P2, and remember, please, that the dual lattice is generated by things called L1 and L2. Yeah? Okay, so now we're going to work in spaces like this. These spaces are doubly periodic functions. Okay, and now I can come to the theorem which I talked about here. Let's show you again. This is the Sakharov-Craig-Sulin formulation. And here's my theorem. that the formula for F, which I just showed you, so the Sakharov-Craig-Sulin formulation is F equals 0. Here it is. And this formula actually gives you an analytic function on these from this space to this space. So here n has to be, so n minus 3 has to be bigger than or equal to 0. So n has to be bigger than or equal to 3. Right? So analytic means then analytic for small values of eta and for values of c, the wave speed near any fixed wave speed you want. Yeah, so I apologize for the C0 notation because C1, C2 are the components of C. The C0 is a fixed value of the vector C. So next time maybe I'll underline the C0 and the C here on the screen. You can see it really clearly, but you're a bit of the same, right?
Why do you drop the forward roots?
Because the U has water routes in it. Yeah. If it's water waves, then it's n-1. Yeah. The whole thing works for water waves as well. But I'm trying to put to show how to do it for hydroelastic. Okay. So obviously, the main point here is how L depends upon eta. And so here's the theorem for that. If you take a slight generalization of the L where you change that eta to zeta, this is just because G minus 1 is kind of a boundary value problem. So it operates on some data, and data here is called zeta. In the version we want, the zeta is actually the same as eta. And the main point is to show that that's analytic in suitable function spaces. Here you don't lose as many derivatives. Main loss of derivatives is from the U, as you saw. And in their paper, David and Walter look at G, not G minus 1, and they prove a result similar to this using boundary integral representations of G. I've got a cheap and cheerful method of showing this result, which is very, very simple and suitable for our purposes. So you can actually simplify their work hugely in this extent. This is not belittling their work at all. This is a cheap and cheerful thing, which is suitable for what we want to do. But I won't show you the proof of this because, it's not difficult. It's only 2 pages on here, but, it will distract us a little bit from the point. But I have it on, I actually have it at the end if anybody wants to see it. And again, it will be in the all right. So let's just take it for granted that F is analytic. Okay, it's a big ask, but I mean, I've told you that I can prove the theorem. Okay, so this is the heaviest page. What you need is a local bifurcation theorem. Here it is in its form. This is a work in progress at the moment. So I'm not sure if I formulated everything in the simplest possible way. But you will see that this theorem applies and will give us the doubly periodic waves and will stop us from making the similar mistake to the one we made before. Because remember, there are still 2.5-dimensional waves around here lurking to bite us if we're not careful. Right? So in general, so let's take an analytic function in some space, Hilbert space X, to some Hilbert space Y with 2 parameters. Those would be, so in our problem, the elements in X would be eta, and the elements in R squared would be C1, C2, yeah, C. Okay. What you want then is for there to be 2 subspaces of X and Y. Let's call them X1, X2, Y1, Y2, which are invariant under F. Invariant in the sense that X1 goes to Y1 and X2 goes to Y2. Invariant is the wrong word, I know. So they're kind of like, there are special classes of solutions. Yeah? And then you take an X1, your X1, which is orthogonal to X2. You take an X2 and X2, which is orthogonal to X1, and the same for Ys. Now, so it's not as scary as it looks, right? Now I'm going through it, it's not scary at all. And then a certain value of the bifurcation parameter. What you want is for the kernel of the linearized problem, linearized F. So this is just a linearization at 0. You want that to be 2-dimensional and spanned by these X1 and X2. Now, in a standard, in the Crandall-Rubinowitz stuff, this will be 1-dimensional. So now we're going beyond Crandall-Rubinowitz, that's the point here. And you want Y to be given by Y1 and Y2 plus a complement, and the complement has to be the image of this operator. I said this maybe the wrong way around. Maybe I should have said the complement of the image is spanned by Y1 and Y2. This is an orthogonal direct sum. So for those of you that want to hear this more mathematically, I'm saying that L is that LC0 is Fredholm with index 0, and the dimension of the kernel is 2. That's what I'm saying. Yeah? Okay. So, okay, that's relatively easy to understand. And then there's a transversality condition. There always is in this type of theorem, you know. And the transversality condition is like this. I put this, I think I've written this in a bad way. So what you want here is a determinant of a 4x4 matrix not to be 0. So what you do is you take the linear operator, remember C is 2-dimensional, so you take the gradient with respect to C, yeah, and evaluate it as C0 at your parameter value. And then I've written down here a scalar product Y1. What I mean is you take the scalar product of the first component, and that goes in the top left, and then you take the scalar product with the second component, and this goes in the top right. This is really bad notation. I should have written 4 entries here, but I was too.
So I mean, it's a block diagonal matrix.
This is a 4x4 matrix.
Right, but isn't
Just a 4x4
but the
matrix.
invariance is reduce the dimension? Oh, because
It's just a
it's
4x4
basically
matrix.
the Rabinowitz, random Rabinowitz condition generalized.
It's exactly what it is. And this is just a generalized Rabinowitz theorem. That's all it is.
They had a multi-dimensional version. Came out in the year or two later.
They did. This is the simplest version of that I can do. Yeah. This is the simplest I can do.
Yeah.
Yeah. So that's the whole point of what I'm doing today. I'm trying to tell you that something that looks complicated is actually simple. That's what I'm trying to do in both parts of the talk. I don't know if I'm succeeding afterwards, but okay. All right. And the theorem says, well, under those conditions, you get an analytic branch of solutions like this, parameterized by perturbations of C from C0. So T is a vector, 2 components. And in particular, you see at linear level, it's T1 times X1, T2 times X2. So provided you make sure that T1 and T2 are not 0, you will really get a 3-dimensional wave. You're not going to get something which is 1.5 dimensional, 2.5 dimensional. Okay, so now all I want to do now is to show you that this theorem actually applies. So now I know it's a lot to take in, and I know it's the end of the morning. All you have to remember here is you've got special spaces of solutions x1, x2, y1, y2, with special vectors in them called x1, x2, y1, y2. Kernel is x1, x2. And then you've got some horrific transversality condition, which isn't so horrific after all. Okay, so let's go back to what we had before. So here's our spaces of functions. We write them like this. The doubly periodic way. I've got the lattice here again. Here's the reality condition. You have to have this, obviously, because eta has to be real. And again, I've told you what x and y have to be. They fit in with what we had earlier. But again, it's not important. Now, one thing you have to do here, because the dimension actually would turn out to be still too big, is you restrict to even functions. Even means invariant with respect to x goes to minus x. In terms of the Fourier coefficients, this will give you eta k is eta minus k. So if you go for even functions, you're going to get eta k is eta minus k is eta k bar. Okay? And the x1 and x2, well, it's no surprise. What are they going to be? The spaces of special functions, where you see you want to get rid of the, you've got these 2.5 dimensional waves. In particular, you've got these 2 directions, P1 and P2, and you can talk about waves which are periodic in P1 but constant in the P2 direction, or waves which are constant in the P2 direction and periodic in P1. And that's what the distinguished spaces X1 and X2 are. So X1, those are waves which are constant in direction P2. They will have the property that that the coefficients will be 0 if K dot P2 is 0, is not 0. X2, those are waves which are constant in direction P1. So I think I chose the notation in the right way, right? Because X1 means you're only periodic in direction P1. And X2 means you're only periodic in direction P2. I kind of formulated it in a negative way here. All right, so you've got the setup, you've got your spaces worked out, and you've got these 2 distinguished directions, which are the trivial periodic, doubly periodic directions. Okay, now we come to this is already the smiley, so you see we're already, okay. But again, I packed a lot onto this slide. The Americans usually say this is a busy slide. That's like, I try to avoid Americanism, sorry, Katie, but I really like this one. This slide is busy, and it is a bit busy. Okay, so here's our representation again. So what you do, you work out how the linear operator works on eta. Now, when you linearize everything, at whatever level you do it, you're going to be talking about a linear boundary value problem in a fixed domain, and you can solve it using Fourier methods. It's not difficult to show that the action of the linear operator on eta is given like this. So eta 0, it's a Fourier multiplier. Eta 0 just goes to eta 0, and the higher modes get multiplied by this dc, which is given here. You recognize dc again? We've had it today once already in a different form. This equals 0 is the dispersion relation. So in fact, the linear operator is just multiplication by the dispersion relation. Okay? Now, working out the kernel is a relatively easy thing. So here I've done it. So if you want this to be 0, then you're obviously going to have eta 0 to be 0. And you're going to have to put all the eta k's equal to 0, except for the ones where dc of k vanishes. So like this. No? So the kernel will be the sum of everything for which the eta 0 has to be 0. Otherwise, you want the dispersion relation to be 0. And it has to come in this form because of the reality condition again. And you can see here, obviously, if k solves this, then minus k does as well. No? So this is, this is kind of, in German we say doppelt gemoppelt, which means I've actually written the same thing twice here, because if I'm taking this away, it's still right. Yeah, yeah. Okay, it's a good expression, right? Busy and doppelt gemoppelt. Okay, so, all right, so let's see the implications of this. Let's go to real coordinates. We got eta k bar here. So instead of writing it in this form, I could write it as the span of cos kx sine kx with the same relations. Yeah, you see, I don't want to write span here because of the reality condition. You get in this complexification, verification. Students hate this. My student hated it, so he wrote it like this, which I thought was very clever, avoiding the whole issue. This is obviously just the same as with the cos and the sines. And then if we restrict to even functions, everything invariant at x goes to minus x, then this kills the sine. Now we just have the cosine. Right? So the kernel is given by the span of the cosines here for the case which the dispersion relation is 0. Okay, so we know what the kernel is, and now I'm going to persuade you that the dimension of the kernel is in fact 2, and that the transversality condition is satisfied. First, let me make a slight technical detour. Using this representation as well, you can show the other part, which is that this thing is actually Fredholm with index 0, using the same formula. Essentially, you have to show that this thing has compact resolve and something along those lines. So I'm skipping that part. Okay, so let's look at this. Now, I think this is actually, I think, the same argument as in Walter's paper with David, but it's written a little cryptically there. Well, in a very compact form. And here it's a case of a diagram says 1,000 words. So let's see how to do it. So which values of k? The question before the house is which values of k have dck as 0? That's the question here. Okay, so let's look at dck is equal to 0. So take the equation. Dck is obviously the same thing as c dot k is plus or minus this thing to the 1/2. It's just now at school level mathematics. Hoping I got it right. I forgot the cost. I got it wrong. So okay, so I failed my GCSE. Okay, but it's the first typo so far, right? Which is pretty. Nobody spotted it, right? So that's not bad. I don't know. On the last. That's okay. So, what does this tell you, right? So let's look in the C1, C2 plane. These are the components of C. So here I've got C dot K is plus or minus something. So this says that C lies on a line in that plane, which is perpendicular to K. Okay, so here you can see some lines which are written down here. Right? Now, so if I want this to be 0, then I have to take C to be on some line in the plane, and it will always be one of the lines will always come in here. So here are two possible lines corresponding to different values of K. Now, the point here is, if you look back to the construction, you can always take as your choice. So let's put this a different way. If you give me a K, then I just have to make sure that I'm on this line. So I can look at it the other way. If you give me a k, I can choose c to make it happen. But I can always choose for my k's L1 and L2, which were the generators of the lattice, of the dual lattice. And then L1, L2, those are linearly independent. So I will get then altogether 4 lines like this. And what I want then is for C to be simultaneously on these things. So I'm going to get in general 4 points of intersection, and I can choose any of those points of intersection, and it will give me then a 2-dimensional kernel corresponding to those two lines. Yeah. So in general, the kernel will indeed be 2-dimensional, given like this, if I choose C0 according to this picture. Now you might say, well, couldn't there be other values of L which also intersect this line at that point? And there could be, but it's non-generic, right? Because if you just give me straight lines, generically they will intersect in one point. You could be lucky or unlucky, depending on your point of view, and they can be parallel. But if two intersect in a point and you draw a third one, then it's non-generic that that third one goes to the point. Of course, we could fix it so it happens. But generically, you're going to have a 2-dimensional kernel, and wave numbers you want here are the ones which come from the dual lattice. Okay, so with that choice of C0, C is C0, we have what we want for the kernel. And now we just have to check the transversality condition. So we're going to put x1 to be this, x2 to be that, and the y1 and y2 to be the same. This is slightly wrong, right? Because x1 and y1 are not in the same space, so really they can't be equal. But I mean, you know, this isn't a typo. We're all among friends here, so we can accept that. You can calculate the matrix here explicitly. This is again just a calculation. So I've done it. Look, I remember the cost this time. It's interesting. This determinant is non-zero. Why not? Because L1 and L2 are linearly independent vectors. All I've got here is an L1 across the, well, so it's really L1 transpose. I mean, I used the gradient in the wrong way here, right? I mean, it should be 2 by 2, so this should be L1 transpose, which is L1 times a constant. This is L2 times a constant. So the 2 rows here are linearly independent, which means the determinant is non-zero. Smiley. Congratulations, you have now proved the existence of doubly periodic waves using a second method. And you can choose the method as whichever the methods as you want. And you will avoid 2.5-dimensional waves because of that here. The parameterization will make sure that you don't run into this method. Of course, you can always take T2 equal to 0, and then you will get the 2.5-dimensional waves, or T1 equal to 0. But if you don't do that, you're going to get a family of doubly periodic waves. Okay, so Smiley is a good place to stop. That's all I have to say. Thanks very much.
Questions?
Another question. So both methods deal with the distance of
Just that's correct. That's correct.
Perturbative.
That's correct.
So there is no results about
No, there aren't. No, there aren't, and it's one of the big open issues. But it's been open for a long time. It's only been in the last couple of years that computing methods have developed to actually compute them more than small amplitudes. Now there are quite a lot of good people working on that. David Nicholls himself works on that, and some guys in the UK, Pomilewski, John McLaren and his collaborators, they work on this type of problem. So although they're mainly interested in solitary waves at the moment in 3D. But you put your finger right on the point. One of the big open questions is how to, if you like, how to continue the local bifurcation to a global bifurcation. It's as far as I know, it's completely open. Yeah, that's right. I can do better. I can do better with the analyticity. I can prove analyticity away from 0 as well, but not with such a simple method. I was going to say, as I showed you, but I didn't show you. Not with such a simple method as I didn't show you.
No questions? Do you have anything in mind?
No.
Okay, let's take the mark again. why wasn't, I thought e to k is real, isn't it? E to k is real, because you have e to k is equal to e to minus k.
They are for the even functions, yes.
Sorry?
They are for
No,
the
I
even
thought that
functions.
earlier you'd shown that they were, maybe not.
No.
Yeah,
E to
e to
minus
minus
k
k
is
is e to k bar, restrict to even
And then
functions.
if you have the even functions in the real.
But then I thought you were restricted to even functions subsequently.
I did, but I
Not.
had a couple of things in this slide at once, you know. This slide was very busy.
Really getting some mileage out of that.
Yeah, really. Yeah.
So there's really no restriction on the gamma you can choose then? Or
So the theorem kind of says, give me a gamma, I can find a C0. That's basically the theorem. Yeah.
yeah, because it'd be interesting at some point to see the bifurcation curves that come out of this as a function of gamma.
Yeah,
Right.
really good, yeah. Yeah.
Wait, as a function of gamma, but
Yeah, the rigidity.
oh, right.
The whole gamma is kind of fixed, and, you know,
Yeah.
but it's really fixed gamma, and then you can find a C0. This one's-
Mhm.